Most of the substances that we encounter are compounds. They are not pure elements. We actually encounter very few elements in everyday life. We've talked earlier about the difference between a compound and a mixture. So both of them are going to have more than one element, right? But in a compound, we have them in a very specific proportion. And all the individual particles, if you could just zoom in and look at the individual particles, all the molecules would be the same. In a mixture, you're going to have two or more different kinds of atoms or molecules, and the proportions can vary. So here's an example with hydrogen and oxygen. So here we have a balloon full of a mixture of hydrogen gas and oxygen gas. The properties of these two elements, when they are just in a mixture, they retain their original properties. They're both gases, and they will combust. Right? You light a match to that, it's going to go kaboom. Here is a balloon also filled with hydrogen and oxygen. But here the hydrogen and oxygen are in a compound called water. There are two hydrogen atoms for one oxygen atom. All the particles, all the molecules are the same. In this balloon, we could have added a little more or a little less hydrogen gas for the amount of oxygen. It'd be fine. You can't do that with water. You can't adjust the proportions. They are fixed. This balloon will not explode if exposed to a flame. And the first time I saw this picture, I looked at that for a while. I'm like, what the heck am I looking at? So this is a picture taken like just fractions of a second after this balloon is popped. So the water is just starting to splash out. The balloon's pulling around this side. So if you're wondering what the heck that picture is. So Joseph Proust, back in the 1700s, early 1800s, was the first one to formally state the idea that elements combine in fixed proportions to form compounds. And this was stated in the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. And this is before we knew what was inside of an atom, or really even what atoms exactly were. But what they observed was that it was the same proportions by mass. If we take a sample of water that weighs 18 grams and we decompose it, we can do that by passing electricity through it. And if we collect the oxygen gas and the hydrogen gas and determine their masses, you'll get 16 grams of oxygen and 2 grams of hydrogen. And the ratio there of grams of oxygen to grams of hydrogen, 16 to 2 is 8 or 8 to 1. It doesn't matter what sample of water you take, how big the sample is, how small the sample is. If you decompose it into hydrogen and oxygen gases, the ratio of oxygen by mass to hydrogen is always the same. That is characteristic of a compound. We say it has constant composition. The reason is that the water is a molecule composed of 2 hydrogen atoms and 1 oxygen atom, and it's always the same number of atoms of each element. Now it's 8 to 1 oxygen to hydrogen, even though it's 2 hydrogen atoms to 1 oxygen atom, because the oxygen atom weighs a lot more than the hydrogen atom does. Let's look at this example. 2 samples of carbon monoxide obtained from different sources are decomposed into their constituent elements. One sample produces 4.3 grams of oxygen and 3.2 grams of carbon. The other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? Well, what's the law of constant composition? It says the ratios are going to be the same. So the ratio by mass will be the same. So let's look at our first sample. Maybe we'll call this sample 1. And it had 4.3 grams of oxygen and 3.2 grams of carbon. That's not what I wanted. What is wrong with my head? 4.3 and 3.2. Okay, and then sample 2, 7.5 grams of oxygen and 5.6 grams of carbon. Well, just looking at those numbers, those are messy numbers. It's hard to compare them, right? Let's look at the ratio. Oh, I forgot the units over here. Good grief, losing it completely. Okay, so what would 4.3 divided by 3.2 equal? Well, that is 1.34375. And let's do the same ratio over here. 7.5 divided by 5.6. This equals 1.339286. Are those exactly the same? Not exactly. Are they really close? Yeah. These are measurements. There's uncertainty in the measurements, and these are not even very precise measurements. 4.3, that's to the nearest plus or minus 0.1 grams. And so if we look at significant figures, what happens? Well, 2 sig figs and 2 sig figs, we're dividing them, right? So then our answer should have the same number of significant figures, 1.3. So this is 1.3. And over here, again, 2 sig figs, this one should have 2. And now, within the uncertainty caused by the measurements, they are exactly the same. So, are these results consistent with the law of constant composition? Yes, they are. 2 samples of the same compound from different sources, you decompose them, you look at the individual parts, and they have the same ratio.